maybe just two comments. The first question I was asked, which is, of course, fully justified. We always try to minimize cost functions. Now we're maximizing cost functions. So the point is that, of course, minimizing, let's say, maximizing f over something versus minimizing minus f is identical, okay? These are identical mathematical things. In the beginning, we just try to always bring it to the same form so that, like, whenever we write down, you get woken up at midnight and says, this is the cost function, you always know you have to minimize, you don't need to think about it, okay? It's just that here it's kind of, it's the literature typically, particularly when you're talking about maximum likelihood, it's called maximum likelihood. So typically people maximize, okay? It's not called minimum minus likelihood. So it's just that, we didn't bother now writing a minus and then minimizing, okay? So I hope, of course it would be nicer if I always stick with the same notation, but then you get a lot of minuses and you get a lot of extra things you have to work. The other one was the question is, what's the point of, I always try to make the point that it's good if we can get to the same cost function, the same optimization problems in many different ways, right? So think of least squares. We had an interpretation probabilistic or geometric, and the same thing was true for nearest neighbor and so on, okay? So why is it good that we have that? The point is like the following. Of course, in machine learning, the difficulty is it's an accumulation of methods, and what makes it difficult conceptually is that we don't have the one model that we know is absolutely correct, is simple, and then we just optimize the heck out of it, right? So we have to come up with model. We have to come up with reasonable things where we're saying, okay, assume the data came or it was distributed in the following manner or had the following distributions, and then under certain assumptions I can then derive what is the best thing given the data now to do the optimization, right? What are the optimum parameters to do the classification or whatever it is that I'm interested in. Now, since all these are just assumptions and the only kind of proof at the end is whether it works or not, it's of course nice that if we knew that whatever we assume doesn't really influence at the end the result that much, right? So if I had like 20 different models for some particular data and they all tended or pointed towards me to optimize the same cost function, right? If they all lead to the same optimization, then I know that it doesn't really matter so much if I assume the data came from this or came from this or came from this or this. If I want to have a good classifier and I want to find a good parameters, I should always do the same, okay? I should always minimize this cost function. So in that sense, this gives me confidence that my result is robust and is not too dependent on my assumptions, which after all, I'm just guessing, okay? It's just experience, I'm guessing, I'm making it up as I go, right? Now, of course, on the downside, if all of these lead to the same thing, if I wanted to have interpretability, right? If I wanted to say, oh, this means the data has to behave like this. If I have 20 models, all of them give me the same, that actually gets worse, right? Because it just means I can't really say much, okay? But right now we are more concerned about making good predictions, coming up with good classifiers or good regressors. So let's go back now to our problem. We just have to do this one extra thing, and then we have to interpret. So for this one, okay, I'm sure you figured it all out, but just in case, okay, how do we get this? Okay, remember that the determinant of a matrix can be written in the following way. I can expand by any, let's say, row, right? And then what I have is I'll just have A, I, J, where I go over all the rows of J, and it's times these cofactors, okay? So I have C, Cij. Okay, and what is a cofactor? So this determinant can be written as going over picking one row, this is the ith row, going over all the elements j, and then when I go over the jth element, I'm scratching the ith and the jth, I'm scratching the ith and the ith row and the jth column. I compute the determinant of what's left, and then, so this thing here is the determinant of this times a factor minus 1 I plus j. Okay, so this is something all of you have seen at some point, okay, in your linear algebra days. And so you also have seen, of course, how to compute an inverse, right? And a way to compute an inverse is simply the following, is it's also equal to, sorry, so if I take the inverse and I'm looking at the things ij, this is also cji over the determinant of A. Okay, so both of them are related, computing the inverse and computing the determinants. So if we remember this, right, then this is fairly clear, right? Why? Because if I'm taking the derivative with respect to a component here, this is just some function that depends on these components here, right? And so what is it? It's always the log always gives me 1 over. So this just comes from the log. And now I need the inner derivative, right? But what is the inner derivative? Well, we just wrote down that this, this is the determinant. And so I need to take the derivative with respect to one component here, right? And so let's expand it out. If I want the derivative with respect to ij, let's expand it out by the ith row. And then there's only one term that depends on ij here, right? That's this term. And so I get here Cij, okay? Cij. I'm somehow not happy. Just hold on a second. Yes, okay, so I get Cij. And so now what is this if I'm looking at this thing here, right? So this, the ith term is simply this. This is always the same. It's the determinant, I get this term. But now look at what this is, right? So this is exactly like the inverse of the matrix. The ith j term is exactly the inverse, except that here you have ji rather than ij, right? So this means that this corresponds exactly to the a minus 1, but now ji, okay? Not ij, but ji. So it's just a transposed, right? So, and this brings us exactly to this thing, so that if I take the derivative of this, this is just the matrix, the inverse matrix, but transposed. Now, since for us, all the matrices are symmetric, the transpose doesn't matter. We'll just get minus in there, okay? We just get the inverse of the matrix in there. Good. So now let's get to what we want. So we just have to do the last part. We have to take the derivative with respect to this thing here. So with respect to the covariance matrices. Now what we'll do is the following, okay? This depends on the inverse of the covariance matrix. So let's just take the derivative with respect to the inverse of covariance matrix. Now here we have the inverse here. Here we have this thing here, right? But remember that if this is an invertible matrix here, right, that of course the determinant of the matrix is just 1 over the determinant of the inverse matrix. So this is exactly the same as having here minus 1. Okay, so now we have both times the same matrix, which is convenient. Okay, so taking now the derivative here, again, I'm just writing it down here like this. Right, so what do I get? I get again the sum. I get again the kth term. I get again the q and k t plus 1. And so now I get 2 terms, right? The first one will come from this one here, right? So I get here, what terms? I get a half. And we just wrote down that the derivative of the log of the determinant of the matrix is just the matrix, the inverse, okay? But that's already the inverse. So what I'm going to get is just the matrix. I also get the transposed, but since it's symmetric, it's already the transposed. Okay, so I get just this. Okay. And now what about here? I take it with respect to this, right? So this will just give me minus a half. And what do I get here? Xn minus mu k. But this is now, so this was the transpose, not the transpose. I get the outer product times xn minus mu k transposed. Right, and this is equal to 0. The half I can cancel. And so if I write this now all down, okay, then I just want to write it next to this thing here. I get that the sigma k is what? Okay, so this again comes out because I take the sum here, and this is now at time t plus 1. So this is equal to the following, is equal to the sum of n is 1 to n of x n minus mu k. Okay, sorry, I have to delete this, times x n minus mu k transpose times the q n k at times t plus 1. And then I just have to again normalize things. Okay, so let's just check that I got this all right. Looks reasonably similar. Okay, so everywhere there should be, so sorry, there should be everywhere times here. So this should be everywhere there should be times in here. So there's everywhere a time. This is again should be a time t. This should also be same here, time t. And the rest I think is all fine. Okay. Any questions? So let's go over. So here we have the whole algorithm now written down, right? I start with some. So this is my set of parameters. I start with some initial set of parameters. Maybe the pi's are uniform. I pick somewhere the mu's, and I pick maybe these are identity matrices, and I pick somehow the mu k's distributed somehow uniformly over the space, right? And in order for this to work well, people have thought about it, how to do this, but right now we're not discussing this. Once I have this, I have already my one set of parameters here. I want to find a better set of parameters. So I first check that with the current parameter, how well I'm doing. I'm plugging in all these parameters. I check how large the cost function is, right? And the cost function is the log of the likelihood. Then what I do is I'll construct a good lower bound, a lower bound that's tight for this parameter that I have currently. And I do this by constructing these auxiliary random variables here. And out of this now, this is now my lower bound. And this lower bound, if I plug in my phi, my theta t at the current time, I get exactly back what I had here. Okay, but now I'll think of these parameters again as free, and I try to find better parameters, fixing the t. The t is fixed, and so now, or the q, sorry, is fixed. The q's is fixed. So now based on these q's and these other ones, I can plug in, I get the nu pi's, the mu mu's, and the nu sigmas here, right? So now I have a better set of parameters. If I plug this set of parameters in here, so now this is theta of t plus 1, I'm guaranteed by the construction that the nu, right, that this sequence, if I'm looking at L of theta 0, right, this is smaller equal than L of theta 1, right? And so this is, I'm guaranteed that the sequence is monotonically non-decreasing, okay? So it's an increasing sequence in t, right? And that's good because I want to get my, I want to maximize the log likelihood, right? So I'm guaranteed to, at any point in time, can only do better. I'm not guaranteed to converge to the optimum, similar to what we looked at k-means. And so what you just guaranteed is that you will converge to some local optimum solution of the maximum likelihood. And also, of course, you can construct, again, very bad examples where it takes a long time to converge, but that's not typically what you see in practice, right? Same thing with k-means. We didn't really talk about the convergence, but if you have bad luck, you can construct malicious examples where it takes you an exponential time to converge to some suboptimum solution. But these are rare cases, and you can make this mathematically precise. Okay, so these are really contrived cases. And if you look at these cases and you just vary things by the tiniest bit, typically they behave much better. Okay, so it's something called smooth analysis where you can actually show that the cases where it's really bad are rare cases. So it's not typically what you have to worry about. That is the EM algorithm, the way we present it here. Any questions about this? The rest what we want to do is we want to now interpret it and bring it into the form that typically you see. I think once you have seen it like this, the other part is also fairly clear. But I think that this is clearer. The other part is probabilistic, and I think it's a little bit more confusing, if that's how you see it first. So before we go to the confusing part, yes?
When optimizing sigma k at time t plus 1, shouldn't we better use mu k at time t plus 1?
Yeah, I think this depends. I mean, actually, if you want to have the guarantee, okay, I think in the notes that's how I wrote it. But I think it's actually, if you want to have the guarantee, you better use just the old parts, because that's how we derive things, the condition, okay? If you want to know that you're increasing. In practice, you're probably right that you probably, it's better to always right away use that, but it might be harder then to give guarantees, okay? So in practice, you might very well do this, that you take the pi, and then you, based on this pi, you compute this, and then based on that. But if you want to exactly keep that logic here, right, you know for sure that that's true if you just optimize, pick the globally thing and have it. Okay. Yes.
How can we choose effectively the initial choice?
So I think again, for example, for k-means, right? If you think of that, one option is you just choose them randomly. Okay. That's not the best one. There's something k-means plus plus, in which you're trying to spread things out a little bit. Okay, so you choose maybe the first one, and then the second one you don't choose again with, let's say, a Gaussian probability, but you choose it actually conditioned that it is reasonably far away. So you want to spread them out. And then for this kind of initialization, you can prove something. Again, the guarantee is not very strong, and in practice, typically you do see much better. So it's interesting theoretically, but that's the initialization that you will, for example, if you use that in Python or something, that's typically the initialization that's used, okay? So here again, you would assume that probably the pi you should choose uniform, because if you have no assumptions about that some of them are much more dominant than other ones, there's no reason to assume that some are huge mountains and some other ones are small ones. You probably would assume that the sigmas you should use uniform, again, unless you know that there's, that things have a certain directionality. If you don't have any prior knowledge about it, then it's the kind of most canonical form, right? But you would assume again that the means probably should be somehow spread out, right? And not just all clustered together, because then it might be difficult to first decluster them. Okay? And I'm sure that people have come up with all kinds of heuristics to do it better, and might also depend on the case. Okay, any other questions? Good, so now let us get to the interpretation, right? So I hope it's clear what the M is in EM algorithm, right? The M is exactly what we did in the last half an hour. It's the maximization, right? The M is exactly this. That's the M, right? We maximize these parameters. What's completely unclear is why this step is called the estimation step, right? Where's the estimation? We constructed a lower bound. No estimation seen anywhere. Sorry?
Expectation or estimation?
Expectation. Did I say estimation? There's no estimation either, so, Okay, good. So it's expectation maximization. Okay, so the question is where does the expectation come from? And so what we'll argue now or see is that actually this thing that we constructed here, that is actually an expected value. Okay, so what we called the lower bound is actually an expected value. But what kind of expected value is? What is the model here? Well, remember, so our original Gaussian mixture model, right, was that if I have a data point, I have some probability that my data point comes from the kth Gaussian, right? And then given that it comes from the kth Gaussian, I have a Gaussian distribution, and this Gaussian distribution has some particular mean, and it has some particular variance. Right? So I have already around these random variables, which you know, this thing that asks me, what is the chance that a certain data sample comes from the, you know, the cave thing of the Gaussian, right? But these are prior probabilities, right? So this is averaged over all the data that I have. So the question is, so this is kind of the prior. And, you know, so of course, this I should write it like this. This, of course, still depends on these pi's, right? So this thing depends on the pi's. So there's the condition on the pi's, which has some fixed parameters here and here. And of course, we know that this was it's exactly equal to this pi k. But of course, I can also ask, what is the chance that my data point comes from k if I now give you actually the sample? So that's the posterior, right? So now you observe the sample, right? And you ask. And so, I mean, it's quite clear, right? Think of, for example, let's say you have two Gaussians. It's a mixture of two Gaussians here, right? And you get now some data point, right? And maybe I give you a data point here, right? And I ask you, is it more likely to come from this Gaussian or this Gaussian? What would you say? Let's assume this is the mixture of the two, right? Intuitively, without writing things down. And now I give you a point here. Is it more likely to come from the right Gaussian or from the left Gaussian? Right? I mean, intuitively, it's pretty clear it comes from the right one. So let's just do this, right? So this is just equal to the joint one, right? Divided by the so I'm just using here Bayes' law, right? Just to write this down. Now, of course, this is just a parameter here. Whatever the distribution I assume here, this will cancel out anyway. Doesn't matter, right? So I can just write it down like this. OK, so now what is it, right? This is exactly this here, right? So that's fine. So I know already what the bottom is. It's just pi, let me write it here, j, so that we don't always get the same, pi j of this n of x, and then mu j and sigma j. Right? So this we already know. And what do I get now on the top? Well, so now I just get this pi, right? Sorry, I get I get pi times then so I get this, right, which is again this pi, and then I still get the x given the condition, so I just get this k times eta of x and mu k. Right, so this is my posterior distribution. So if you fix the parameters, so now the theta is fixed, and you give me a sample, and now you're asking me, what is the chance that this comes from the cave Gaussian, right? Then what do? What is this product here, right? The product here is exactly the height of these Gaussians here, right? Because this is the Gaussian times the prior, and this is exactly the height. So you're simply comparing the heights of the two, and then you normalize by the sum of the heights, right? That's exactly this. One of them, this is just the height of the cave one, divided by the sum of all these normalization constants, right? So it's very natural. Clear? Right? I mean, how would you have, for example, if I've given you something here, would you have told me this belongs to the left or to the right? Right? What you will always do is you compare simply these two. If it's two, you will exactly compare these heights here. And, so this is exactly the threshold here, right? If you're more on this right side, you assume it comes from here. It's more likely to come from here. Here, it's more likely to come from here, right? And the posterior probability is exactly the height of one divided by the height of the two, right? That's exactly the two probabilities that you have. So this means, but what is this, right? Well, we have seen this somewhere, right? It looks suspiciously familiar, right? And what is it? It's exactly the Q and K, right? So these Q and Ks, which for us were just some random numbers that we had put in here, distributions that simply helped us to find a better bound, these are really the posteriors of the distribution. So the logic is that, rather than maybe a Gini give you this, right, that once you have a set of parameters, you can compute the posterior, right? But now, so now we still need to see, let's assume you had the posterior, right? So let's assume I told you the posterior here. I told you, a Gini told you that the chance that this comes from the kth Gaussian is whatever this Q and K here is, right? Let's assume a Gini told you. Then what would be natural to maximize? What would be natural to maximize would then be the expected value of this likelihood, right? So if you had this, if you had the posterior, if we have posteriors, then it is natural to maximize expected value of log likelihood. Right? But what is the expected value of the log likelihood? The expected value of the log likelihood is exactly this function that we had. Okay, so that's exactly the expected value. So another way of writing this down would be exactly that this is the expected value here. Okay, and but this, this is identical to what we had. There's one difference. There's, if you look up here, you had this log of, this thing here is exactly this, right? It's exactly this here. You still have this term here, right? But this term here is a constant with respect to the maximization you do later on, okay? So this is just some normalization that plays no role when you later on do the optimization. So whether you have this term in here or not is simply you're optimizing the same cost function, just one has an extra constant next to it, which makes no difference when you do the optimization. Okay? So if you think about it now in this way, you can write down the whole EM algorithm in whatever, 30 characters. I don't know how many, okay, something. Okay, so it is, you're working with respect to the Zn given, so what are we having here? The x and the, let me write it like this, the x and the theta t. Just a second. I want the expected value of okay, so written, or if you think about it in this way, then the whole EM algorithm is just this. Given that you have some old set of parameters, you get some posterior on what these Z's are. This is exactly the Q's, right? Okay, now you compute it according to the old parameters. Now you compute the expected value with respect to these posteriors that you computed. You compute the expected value of the likelihood, right? So this is this whole expression that we have written down here. Where is it? This thing. That's just, this whole thing in the bracket with the thing is just that. And now this is with a particular, so this thing here depends on the old parameters. Now you think of this as new parameters, and you find the new parameters that maximize this bound. Okay? This gives you a new set of parameters, gives you a new distribution, gives you a new expected value. You're maximizing this new expected value. Okay, as I promised, that's more confusing. Okay, so I keep the best for last, okay, to confuse you at the end. But I think maybe at best is in the beginning, forget about this, okay? First try to make sure that you understand the other part, and then that's just the interpretation. It is important interpretation because often you will see it written in this form, and also if you apply it to other, to other problems, you will often see it formulated in this form, but it's entirely equivalent. And the first part is certainly much easier and cleaner to understand, okay? There's no interpretation, just a bound, optimize the bound, find another bound, optimize the new bound, find a third bound, etc. That's it, okay? But when you see it described often, so now it should be clear why it's called expectation maximization, because you maximize the expected value, number one. Number two, you also often see it as inscribed as an algorithm in which you add missing data, and then you kind of with the missing data. So what is meant with missing data is exactly you observing the x's, but you're not observing the z's, right? So the z's is just your interpretation. You can think of that the z's were there, but someone doesn't show them to you, right? If they actually were shown to you, this would be easier, right? So a genie just tells you what this distribution is, and that's kind of meant with the missing data, okay? Again, this is only interpretation, yes.
Sorry, for the expected value, is there not a sum over k?
So the expected value is exactly over this, whatever the z's takes on. So that the expected value is this sums, okay? It's the expected value is over everything, the data, whatever you have, right? So that you just write expected value, okay? Clear? The expected value is exactly over the z's that you have in here, right? And the z's take on values k, so that is the sum.
I just mean like the formula that you have over the...
Oh, you're talking about here?
Yeah.
I'm missing a sum? It's not possible. Absolutely. Okay, thank you. Okay. Any other missing parts? Good, so in the notes you see this applied. You see also, so it works of course similar to what you would expect, similar also in k-means. Right? So what it will do is you give it a bunch of data, you tell what the k is, you initialize it, and it will slowly, these Gaussians, will slowly, they might rotate, they might slowly find the right positions, and slowly try to cover the data as reasonable as possible, right? So it's very natural if they have a few slides in the notes, but I'm sure if you just Google somewhere, you will find lots of examples of how this goes as time, right? So in the beginning, you will have some data, you don't know what things are, you get some data, you just get points. Okay, so this is maybe the data you get. Initially, you just assume maybe some Gaussians located somewhere, and you decide where they are, right? And now, as you iterate, hopefully, these Gaussians will move to meaningful positions and maybe also change their variance in order to maybe capture this data in some sense maybe better, okay? Whatever the optimum choice here is, okay? That's all happens. So it's very intuitive what actually happens. Good. That's it. Any questions? We're done, okay?